Off we go. So, hey, last unit, or last mini unit. So, chemical equilibrium has a lot to do with the physical equilibrium we looked at a month ago, where you have two processes happening at the same time, a forward process and a reverse process. Just like with physical equilibrium, we had freezing and melting happening at the same time. Are we ready?
Yes.
And we had evaporation and condensation happening at the same time. Well, chemical equilibrium works pretty much the same way, only we have reactants becoming products and products becoming reactants at the same rate. I think I used the analogy of the Costco last time. If not, let's go over it again. I don't remember which analogies I used in which class. So imagine when Costco opens up, there are more people going into Costco than coming out. And when Costco's closing, there are more people going out of Costco than going in. But during those peak hours, 10 a.m. to 7 p.m., there's about the same number of people going in as coming out. And if you were in a helicopter over the Costco, you'd be like, yep, there's exactly the same number of cars in the parking lot that there was an hour ago. They're not the same cars, but there's the same population. So that's basically how chemical equilibrium works too. Reactants are becoming products at the same rate that products are becoming reactants, but to an outside observer, it looks like nothing's going on, which is why we call equilibria dynamic. It's dynamic equilibrium. Reactants are becoming products are becoming reactants. There's something going on. There's a lot moving. So we're going to add a letter, capital K. It's the equilibrium constant. Sometimes it's KEQ, sometimes it's KP, sometimes it's KC, but it's always a capital K. That capital K is unique to a chemical reaction at a specific temperature. Okay. You want to write that down. The equilibrium constant is unique to a specific chemical reaction at a specific temperature. The chemical reaction will be this K value at this temperature. If you change the temperature, then you change the equilibrium constant as well. The equilibrium constant is unique to a specific reaction at a specific temperature. And it's a number. It's an actual number that we're going to calculate today. Quick review. We talked about this before, but I just want to mention it. If you see something in brackets, that means concentration in molarity. So a 1 molar, this is a 1 molar solution. If you see HCl in brackets, it means we're talking about a 1 molar HCl solution. HCl, 1, brackets mean concentration. Okay. Questions before we jump right in? Give you the big overview. No questions? Okay, wonderful. Moving on. So, why is equilibrium dynamic? Why is it? What does dynamic mean? Yeah, it's movement. Things are happening. Okay, so things are happening. There's reactions that are dynamic. You know, and at the macro level, look down. It's like it doesn't look like anything's happening. But at the atomic level, the reactions are happening. The forward reaction is happening, and the reverse reaction is happening at the same rate. So consider this reaction, this mythical reaction that is A plus B yields C plus D, or A plus B in equilibrium with C plus D. This is a graph of real time of a reaction where the A and B are equal to C and D. Time is on the x-axis and concentration is on the y-axis. So look what's going on. We're starting at time equals 0 with no C and D. And at time equals 0, we're starting with a whole bunch of A and B. And as time progresses, the A and B gets used up, and the C and D get made. The A and D gets used up, and the C and D gets made. Now, we learned last unit that the rate of reaction can be given to us by the slope of the concentration time curve. So if you look at the slope of the concentration time curve, the slope at which A and B is being used up is the same as the slope at which C and D is being made, only they're opposite signs. So their magnitude is the same as they progress. Okay? So the rate that A and B is getting used up is equal to the rate that C and D is getting made, which is pretty handy. And then they enter equilibrium. At equilibrium, the rate that C and D is being made and A and B is being unmade or made back are the same. So the forward reaction, A to B becomes C to D, is the same as the rate of the CD becoming AB. Okay. Give me a thumbs up if that makes sense. That is a question for you. Take 10 seconds and convince your neighbor, at equilibrium, are there more products present or reactants present? At equilibrium, based on this graph, are there more products present or reactants present? Take a couple minutes, a couple seconds. Okay, if your neighbor, based on the graph, if your neighbor thinks there's more products present, do a thumbs up. If your neighbor thinks there's more reactants present, do a thumbs down. What do you think?
I say they're equal.
It has to be one or the other. Yeah. Remember, at equilibrium, it is the rate of the forward reaction equaling the rate of the reverse reaction. We don't know anything about concentrations, but the graph tells us that. The graph tells us the concentrations. Look at the graph. This is the graph of CD, this is the graph of AB. So if you think there's more CD present, give me a thumbs up. If you think there's more AB present, give me a thumbs down. Okay. Looks like most of you realize that there is more CD present. So at equilibrium, all we know is that the rate of the forward reaction, AB becoming CD, is equal to the rate of the reverse reaction, CD becoming AB. We know nothing about the concentrations. We'll use numbers to get those later. Okay? Give me a thumbs up if you understand this. Okay. In that case, answer this question, or these questions. We talked about, is there more AB or CD? We agreed it's more CD. Is A and B at equilibrium, right here, is A and B still being used up?
Yes.
Yes. Because it's dynamic, it's still happening. Is C and D still being made?
Yes.
Yeah. Is A and B being made?
No.
Yes. Because that's the reverse reaction. The reverse reaction is C and D becoming A and B. So at equilibrium, the forward reaction and the reverse reaction are both happening, and they're both happening at the same rate. If that makes sense, then is C and D being used up?
Yes.
Yes. The answer to each of these is yes. At equilibrium, A and B is becoming C and D. At equilibrium, C and D is becoming A and B. In fact, the rate at which the forward reaction is happening and the reverse reaction, they are the same. What's the same, Hayden? What's the same? What's the same at equilibrium? The rate of the forward reaction and the reverse reaction. Do you need a new seat? Okay, pay attention. So, if they do have equal reaction rates, then we can actually write a number that says this is how much each species is present at equilibrium. Now, I am going to show you the reaction rates of the forward reverse reaction. We're not going to meld reaction rate math and equilibrium math in this unit. If you want to do that, take Chemistry AP. They'd love to teach you that. But just remember, the forward rate is the concentration of each of the reactants raised to some exponent that has nothing to do with stoichiometry. Some exponent. So the rate of the forward reaction is K, concentration of the first reactant multiplied by some exponent, multiplied by concentration of the second reactant, multiplied by some exponent. And those exponents, those orders, they have to be experimentally defined. The reverse rate would then be the concentration of what and what? The products. So the reverse rate would be the concentration of C raised to some exponent and the concentration of D raised to some exponent. Okay. that's all we're going to talk about, the forward and reverse rates, because when you take chemistry AP, then you're going to use the math and equilibrium and the math and rates together. But for this class, for the next week and a half, or week basically, we're just going to focus on math and equilibrium. So speaking about the math and equilibrium, give me a thumbs up if you understand so far. You want to see the equilibrium expression.
Wait, hold on.
Okay. So equilibrium expression is pretty cool. It's really, really neat. And it's very, very easy to come up with. Here's the expression. The K, equilibrium expression, is the concentration of the products over the concentration of the reactants. And here's the cool thing. The exponents, in this case, are the stoichiometric coefficients. They are the coefficients for the balanced chemical equation. So the products are C and D. The equilibrium expression is the concentration of C raised to its coefficient, multiplied by the concentration of D raised to its coefficient, over the concentration of A, the reactant, raised to its coefficient, and the concentration of B raised to its coefficient. Pretty handy. And pretty straightforward, too. You will sometimes see the KEQ written as KC, equilibrium for concentration, and KP, equilibrium for pressure. That's just, yeah. Some people like to write it different ways. They're all KEQs. They're all written the same way. They're just giving you a little extra information that says this is the concentration, this is the pressure. All right. Questions so far? No questions? All right, give me a thumbs up if you're ready to move on. All right, so we're going to practice writing. Oh, sorry, ooh, this is important. This is really important. Okay, so for this reaction, before we get to writing expressions, this is important. For this reaction that you told me that there's more CD present than AB. If that is the case, convince your neighbor that this number, and it is a number, is larger than 1 or smaller than 1. Take about 10 seconds. All right. If your neighbor believes that the KEQ value, which is a number, is larger than 1, give me a thumbs up. If you believe if your neighbor believes that it's less than 1, give me a thumbs down. It's like up, up, down, down, up, down, up. It looks like about half and half. All right. This is a mathematical equation that literally is concentration of this, concentration of this, concentration of this, and concentration of this. The y-axis is those concentrations. And at equilibrium, there is more CD. So the denominator is going to be smaller, and the numerator is going to be bigger. This value would be larger than 1. KEQs that are larger than 1, we're going to refer to as product favored, because the numerator is bigger, the product side. So if a KEQ is larger than 1, we're going to refer to it as product favored, in so much as at equilibrium, there are more products present. If the KEQ is less than 1, then we're going to refer to it as reactant favored, because there's more reactants present at equilibrium. And this one is product favored. Okay? Give me a thumbs up, that makes sense. Okay. Now, let's practice writing expressions. Okay, so 2 rules for writing expressions, and they are very, very important. In fact, they make our lives really, really easy. When we're writing equilibrium expressions for substances that are aqueous, we only use substances that are aqueous. If we're writing expressions for gases, we only use gases. Okay, this is important. If we're writing expressions for things that are aqueous, we only use aqueous. If we're writing things for things that are gases, we only use gases. Poor guy. Yeah. It's in his pocket. Pobre. Pobre.
My dad says to me.
One day teaching Spanish woman. That's what you take out.
No, okay. So, if we're writing an expression that uses aqueous substances, we only include aqueous substances. And we're writing an expression using gaseous substances, we only use gaseous substances. Okay. Solids and liquids, their concentration is pretty much infinite, so we just leave them out. All right, let's take a look at this. I'm sorry it's so small. This is 2SO2 plus O2 in equilibrium with 2SO3. So we're going to write our equilibrium expression, AQ, and this is going to be products over reactants. What the product should we write? What's our product? SO3.
Oh, SO3.
And we're going to raise it to the second power, exactly. Why do you raise it to the second power, Mr. Powers? Because there's a coefficient right here.
Oh.
The stoichiometric coefficient becomes the power in the equilibrium expression. And what's one of the reactants?
SO2.
SO2, and we're going to raise it to the second power, and O2, we're going to raise that to the first power. That's the equilibrium expression. Now, I didn't solve it, I just gave you the expression. So that's the setup. Products over reactants. Okay, give me a thumbs up if you understand. Okay, if you do understand, then please do this one on your own. And again, I apologize it's so small, but it's H2SO3, you can always move up, there's always space, plus H2O liquid is an equilibrium of H3O plus HSO3 minus. So go ahead and write the equilibrium expression for that.
No, it's the coefficients that are in front of them.
Why did SO3 get a 2? Oh, that's in front of it.
Yeah.
Oh, okay.
Products is going to be the 2
Mr. Bush, do we always have to write a day?
No, you just use capital J.
Yeah, well, they're also separate. But
What's the name for H2SO3?
H2SO4? Well, H2SO4 is sulfuric acid.
SO3.
This is H2SO3 is sulfurous acid.
Oh,
If we were doing acid and bases, which would be the next unit, I would beg to mention why they're different. But we're not doing acid and bases, so I won't. I'll just let the people taking chemistry 18 learn about that next year.
Wait, so we have to balance what?
Okay, so let's move on. Are we ready to move on? We're good? Okay. So what's one of the products I should write up here?
H3O.
H3O. This is called hydronium. And do I raise it to any powers?
No.
Why not?
Because it's not
There's another in front. And what the other one is
SO3.
SO3 minus, and not raised to any powers
Do you
either.
need to include their powers?
I'm sorry?
Do you have to include their pluses and the minuses?
Their charges. Yes. Yeah, you really should include their charges. Because it is important to remind ourselves and a reader that they are in fact ions. And they are. Okay, how many reactants did you use in the denominator? One. H2O is a liquid, so we don't include it. We're writing a K and Q for aqueous, aqueous, and aqueous. We leave liquids and solids out.
Okay, that's
So that's the K and Q for that reaction. Now we've used the balanced chemical reaction to write a K and Q. We can also go back the other way. For instance, if I gave you this reaction, if I told you the Kp for hydroiodic acid is this, you can give me a chemical reaction based on that Kp. Yes.
But like, if it gives you one like that in the equilibrium expression, wouldn't you not know if there's like one that's not? You know what I mean?
Something missing.
Yeah.
Yes, you would realize that something is definitely missing if it doesn't balance.
Oh.
And that's going to be the case for our third one.
Okay.
This one balances.
This one balances pretty well. Yeah.
Useful.
Does yours look like mine?
Yeah.
Okay. So again, product is HI. The power of 2 tells us there should be a coefficient 2 in front of the product. H2 and I2 are reactants. They don't have any powers, so they don't get any coefficients. How about this one? Sorry if you're in the back. If you're in the back, you're welcome to bring binoculars.
So how am I supposed to know?
Yeah, I know.
Oh, you do now?
Yeah.
Okay. Well, thanks, Kevin.
11.
It's
5, 11, 18.
Okay, so there's something missing.
The last day of Teacher Appreciation Week. I'll meet John's Incredible Pizza.
I appreciate your
John's Incredible Pizza. It's a pizza buffet, and like it's like good Chuck E. Cheese. There's like games and rides and carnival games. It's So John's Incredible Pizza is like kid David Buster's. It's like David Buster's for kids. So it's free to teachers today. So I'll go in. I love it. It's my happy place. That and yogurt. Okay, so. Yes, what? Okay, how do I do? Is this correct?
Yes.
Christians assume it's not correct if he asked. No, it's correct. So, H2O is a reactant. Cl2 is a reactant. The H2O is raised to the second power, so it gets a 2. The Cl is raised to the second power, so it gets a 2. Hydrochloric acid gets a 4. This is raised to the fourth power. O2 doesn't have a power, so it's all by itself. And we can always check our work, because they should, not only should they match, they should also balance. 4 hydrogens, 4 hydrogens, 4 chlorines, 4 chlorines, 2 oxygens, 2 oxygens, and it's balanced. This next one you don't have to do, but I want you to take a look at it. This is the equilibrium for ammonium in equilibrium with ammonia, or ammonium hydroxide in equilibrium with ammonia. That's ammonia, that's ammonium. What's missing?
Oxygen.
Yeah, oxygen's missing, but something else. Remember, these are the reactants, these are the products. These are the reactants, these are the products. Hydrogen's missing.
Yeah,
Hydrogen's missing and oxygen's missing. So what do you think's missing? Water. Yeah, water's missing. So we've got 1N, 1N, 3 hydrogens, 5 hydrogens, 1 oxygen. H2O is missing. Why is water not present in there?
Because it's not.
Because it's so liquid. Yeah. Water cannot be in aqueous with water. Right? Water is just solid, liquid, or gas.
Wait,
Question?
couldn't it be, does it have to be liquid? Like, we know it's liquid, but could it be gas?
It could be gas. Yeah, it could be gas. Either way, it wouldn't show up in an equilibrium with aqueous compounds. Okay. Give me a thumbs up if you're ready to move on. Okay. Now we're going to rub some algebra on it. You have a reaction. Here's our ammonium reaction again. You find that equilibrium there's 1.6 molar ammonia, 0.43 molar ammonium, and 0.22 molar hydroxide. What's the KEQ? Wasn't rhetorical. So grab yourself a calculator and work this out.
I love the
Rhetorical question, like, are you stupid? No, seriously, what's rhetorical?
What?
How long have you been in this class? This is all they're all here.
No.
Yeah.